So up to this point, just as a recap, we've been going through the facilities section. You're in this larger tab here. We stepped through all the buildings. We ended up getting results for all the building types and then each building within there. We looked at that all 2 weeks ago. Now we're going to look at the installation or subsection tab, and really the differentiation between these two. Here we're going to look at we look at the buildings, the facilities, what loads we have that have to be met, our heating, cooling, and electric loads for all of the facilities. And our next step is looking at how we're going to supply or meet those loads. And there are lots of different options. A quick analogy I'd like to make, I think we're all more familiar usually with kind of residential, our own homes. I now live up in an area that I'm lovingly referring to as the Bitter North, and I live in a home that's over 100 years old. And there are a lot of things that could be done, replacing windows, adding insulation, those kind of things that would reduce the energy usage for the home. Unless you're already going to be working on the outside of the home, though, that usually you're not going to see a payback based on the reduction in energy. It's going to cost way too much for the small amount that you would save. But looking at the supply side, sometimes that's another angle where adding something like, for example, changing over an older furnace to a high efficiency furnace. Again, it's going to be close, but adding something here like a wood burning stove or something, it might be much better. So on the supply side, the economics may be significantly better. So there's some things we can do to the building, like changing out lighting. We know a lot of those things that already have pretty good paybacks. But when you get to a certain point, it makes more sense to look at the supply side. And so that's one thing we're going to try to look at for larger scale numbers of buildings together in this section. All right, so getting started, we just start out in this details page, and this is kind of an artifact of the tool in general, and that the loading times used to be very long to get into these, so we ended up just starting here so you could choose where you'd want to go to. There's not too much information displayed here. You've got a little bit of a status screen the same way that you did in the study information, where you'll have a status screen on that very first page that shows kind of how far you are through this process. But at the same time, the way that the tabs are laid out, it really gives you the same status just by looking at the tabs. Just wanted to kind of point out it's there. It's not necessarily critical anymore now that you can see the status just looking at these tabs. So enter this back in. So the first tab we're going to come to is the Cluster and Networks tab. And here really what we're doing is organizing all the buildings for the installation, or whichever group we're looking at, into groups primarily focused on what their heating and cooling systems they have. So let's go ahead in here and create a new cluster. And I'm going to call this cluster Decentralized. And I'm going to end up selecting all the buildings that are currently decentralized. This is the baseline that we're going through and setting up right now. So we went through the baseline for the buildings themselves, and now we're going through the baseline for how those buildings are served or how their energy is supplied. So we're going to see a bunch of buildings on the map here in just a second after we get through entering this information, and we're going to divide them up into these groups. I'm going to select the ones that are currently decentralized. You can add in a description here and select any utilities. Again, this is a little bit of an artifact. It's automatically going to align with the electric utility and natural gas utility that you entered earlier on in the study information. We'll go ahead and hit create. All right, so here are all the buildings that have been loaded up for this study. We can do just a subsection of these in any given study if we want to just focus on some of them. But the way the tool was made, we want to provide the ability to divide up whatever area, it could be an entire installation, into area development plans, into sections we're looking at. These clusters can be aligned with the area development plan, or the SCP, as well. So you can just divide off at this point, still look at a whole installation at the study level, and then divide off into these clusters of buildings down to this level. Or this area can just be for a single sustainability component plan. So here, looking quickly, you can see this kind of group of buildings right here. I know that this group, all of these buildings are served by a central system, and all of the other buildings, you'd have to know this about the buildings by doing the walkthrough, by collecting information. All the rest of them are decentralized. They have their own boilers and chillers that are serving those buildings. So since I'm trying to define this decentralized cluster, I'm going to select all the other buildings. So these tools are very similar to the tools on the map page for the building section. You can just highlight around a group of buildings. You could select them individually or just highlight the buildings themselves in a group that way. I think this is a little easier. I almost always just use the Add to Selection button. So I'll click that again and highlight a few others. And you can see that this area is encompassing some of the buildings that are on that central network, but they're not being highlighted to the different color. So they're not this teal color, which means they're not actually included in this area. This shape is just showing us the overall footprint of the buildings. All right, and these final two buildings. So all the buildings that are this teal color are going to be a part of the cluster. And we're going to go ahead and save those. I've got to move the recorder panel here to get the save button. One more thing you can do is calculate the load information, and we don't have this working automatically because you don't want to reload it every time you select a new building. So once you've selected all the buildings that you want to use, you can go ahead and click this button. Now there's an issue with it right this minute. They're working on fixing it so that it's not providing the right information, but when we hit save, that same information that is correct is going to show up in the cluster in this little summary page. So this is the information you would see if you clicked that calculate, but it's not displaying correctly. This information is correct at this level. So you can see the number of buildings, the ground coverage, so that has to do with this yellow, the shape area. And the reason that's important is going to become clear here in a moment when we look at the centralized buildings. So a lot of times we want to see what the energy density is over a ground space. And that has more to do with the cost of implementing like a central system with a pipeline network and that sort of thing. If you have a large area like this, which is going to end up resulting in a low energy density, we'll compare this energy density here to the density of the buildings that are on a central network, then it's much more expensive and less cost effective to have a centralized network. I think that may be obvious already, but if you're going to put in a central network with a central plant, then having close developed buildings and infrastructure in a small area with a high energy density is the most cost-effective way to do it. You minimize the length of those piping runs, which is really the most expensive part or most variable part of putting in that type of system. All right, so we have all the decentralized buildings. We're going to go back in here and create another cluster and call it centralized. And again, we still have the same electricity and natural gas utilities that we entered earlier. And here, we're going to click Add to Selection and finish putting in the rest of these buildings. Now this is about the simplest case, and the only thing that would be simpler than this is if they were all decentralized. We just highlight all the buildings and move on to that next step. We've had studies that have had as many as 4 or 5 different clusters with different heating and cooling types. So there might be some kind of disparate buildings around the installation that are isolated and they're on propane, a couple that are on fuel oil. There's a natural gas network that has decentralized buildings where they all have boilers on their own. And then some buildings have a central system that they're connected to. So it could be, the complication can go to that level where you have a cluster for each one of those because you're going to be analyzing them differently. But it's fairly easy with this system to just create those clusters and then handle them together, and it keeps it organized as well. So we'll go ahead and save this. And now we can compare kind of the data for even at the highest level for these two clusters. I think this is again what's really powerful about this part of the tool. The same way where we just went through the buildings, and it's a very powerful tool but has a learning curve to it, I'd say the same thing is true about this section. So right away, all that information that has been created or collected from the facility loads has been passed forward into this installation or subsection analysis tool. And we're grouping it together here, and you can see all of this kind of summed up data. So for these centralized buildings, we're kind of zoomed out on it. There are 23 buildings there. You can see this ground coverage square footage. And then we've got data on the loads that has been summed up for all the buildings. So the total electric load over the course of a year is this approximately 18 million kilowatt hours. Do we have Did we have Ben and Chelsea join us yet?
We don't have Chelsea, but we do have Jill.
Okay.
And I'm not sure about Ben.
Okay. Well, we'll have this recording. Just particularly helpful. I think this is a section that that they haven't necessarily used yet, so we'll be going back over it with them shortly as well. Okay, so we've got the total electric load for all of those buildings combined, and then similarly for the decentralized section. So you can see we've got a similar load between these two buildings, between these two groups of buildings. And then similarly, the space heating load over the course of a year, and domestic hot water load and cooling load. So we have all of these listed out. You can very quickly see the numbers at a glance. And then we have densities. So we've got a heating load density and a cooling load density. And again, this comes back to what we want to do with it. If we're doing the baseline, we're only analyzing it in its current as-is situation. But going forward, we're going to look at alternatives and determine whether or not we should change some of these things. Should we try to centralize? And it's very easy to see that this cluster has a high energy density when compared to this because we've got these outlying buildings. Well, if we just zoomed in on, say, this inner group of buildings, we may find that it has a very high energy density, and we'd want both a high energy density and a relatively high energy usage. Obviously, a single building is going to have a high energy density without any other space around it, but we need to have that along with a reasonably high energy usage in total to justify looking into adding a central plant and piping network and all those kind of things. So that's really why we have these metrics here next to the clusters. Similarly, the peak loads. We're going to end up looking at equipment that could be used either for the centralized cluster of buildings. We'll be able to walk through the central plant, see what equipment they have there, and potentially look at additional equipment that we could sub in either when the existing equipment fails or because the economics work out such that it would be better to sub in this new equipment, to purchase new equipment and add it to the central plant even before that equipment fails. And that's where it's really useful to find out what the peak loads are. You can see that this is predominantly a space heating load. That's much higher than the cooling load, and you can see about what the electrical load is. So this would also be helpful in sizing the new equipment. All right, let's go forward to the next step. Feel free to ask questions anywhere throughout this. Let's go to, so we can hit continue. Always make sure we hit continue to go to that next stage. And it's saving all that work that we just did. Okay. So this is going to be a little bit overwhelming at first. This is the list of equipment that could possibly be considered for each one of these clusters of buildings. These are just groups of buildings that we're analyzing together. I'm going to click on the little magnifying glass here to make it a little bit bigger, and we can step through each one of these columns. So right now, let's hit close again. We'll just go over the setup for this page a little bit more. So we've still got our same tab structure here, but now we can change between these two clusters of buildings that we've created. Again, we're analyzing them differently because they have different types of heating and cooling systems. So going through the centralized one, we'll click to make this bigger. We'll step down through all the equipment that we could potentially have. Now, because this is the baseline, we only have the equipment that already exists. We're not going to look at potentially adding anything else until we get to the alternatives. But this list stays the same. And let's go across from left to right on the columns. It's just a regular index, so nothing special here. We've got a couple commands or buttons that we can use. We can delete a piece of equipment or copy a piece of equipment and maybe make changes to it. We have the equipment type. So we've got boilers right away and chillers, and then usually another descriptive name type for the piece of equipment. So this might be the more generic name type, and then something specific. We can say these are distributed boilers. So for the decentralized case, this might be the group of boilers, all the boilers that are used to serve those buildings. Here we've got a field that's supposed to be the max number. It's just abbreviated here. So how many of this piece of equipment could be used in the solution? And it gets a little bit abstract here when we're looking at things like distributed boilers. This is just all of the boilers that would be needed. Here we're looking at systems. So a 10 kilowatt solar system, PV system here. If we were looking at one of the alternatives in the future, and we're going to spend more time on this in upcoming courses, we could say we want to allow our solution to have PV systems involved, and we want to allow up to, say, 5 megawatts. And we could put a 5 right here at the 1 megawatt or 1,000 kilowatt system, and it would allow for that much solar PV to be selected in the solution. What this number is not, it's not the amount that's going to be used necessarily. So we could put, 5s in every one of these in every one of these fields, or a higher number. It's not going to select all that equipment. It's not a simulation. I mean, we're going to talk more about that. But it's allowing the solution to contain this equipment if it's cost optimal. So I think usually it takes a little bit to work through what that means exactly. But just to start off with, it doesn't mean that it's necessarily going to be a part of that final solution. There are ways to force the final solution to include that equipment, but it's not right here. This just allows it to be present. We've got capacities, and we'll look down for some of these things like a central plant boiler. All of these are in units of kilowatts, so this is going to be the output capacity. So the amount of hot water that can be generated, or the amount of electricity. Some of these things, if it's like a reciprocating engine we have here that could produce a certain amount of electricity, and this is the capacity. It would be 300 kilowatts. So this is just the capacity for each item, each piece of equipment. And then I ordered them, didn't mean to. There we go. So what each piece of equipment takes in and what it puts out. And there are some things that take in, everything only takes in one energy source, but some things put out more than one thing. For example, this reciprocating engine takes in natural gas, that's what it runs on, and then it puts out electricity to the grid, and it also puts out waste heat. And this just gives you, let's move that recording panel again, it gives you about the quality of the waste heat. So again, that's more on the mechanical engineering side. It's important to know what temperature that waste heat is going to be at so that we know what we can use it for. If it's below a certain temperature, maybe we can't use it in a distribution network because it's too low and we distribute our hot water at 300 degrees Fahrenheit, and the water is only coming out of this at, say there are lower ones, but maybe it's 270. One of the installations we work with, they distribute at 360 degrees Fahrenheit, which means if we add this reciprocating engine, they can't use any of the waste heat in their network. So that's an important thing to pay attention to, and that's why there are different levels of waste heat. Might be a little bit more straightforward. The next columns are the efficiency. So it's the efficiency of converting from the first input to the first output. So going from natural gas to electricity here, we've got about 28% efficiency for that reciprocating engine. Again, this is kind of it's a nice library to have for anyone that works with this type of equipment. And then the efficiency going from natural gas to waste heat is about 51% here for this piece of equipment. Realizing that doesn't add up to 1, none of our, there's always going to be some additional losses. So we've got efficiencies running down this way, and then an installation cost. So what is the final, just total capital cost to purchase this piece of equipment, the annual operations and maintenance costs, and the approximate lifetime. So that's basically stepping through all of kind of the data we have for each piece of equipment, and we can kind of scan down to take a look at what type of supply equipment are we looking at here. So up front, again, we want to be able to analyze distributed boilers for large numbers of buildings, and we'll show how we cost that and do things like that in a little bit. And then, did we have someone join or fall off? I'm going to guess that was fall off. Okay. So, and then we have distributed chillers. We've got our solar systems that we mentioned before, our solar PV for different size systems. So each piece of equipment, we generally have a couple different sizes, as many as 5 different sizes generally, so that we can capture economies of scale. So larger systems usually cost less on a per capacity basis. So that's why we have a couple different sizes for each piece. We've got basically engines that run on natural gas that are listed here as reciprocating engines. And then we have a group that I'm highlighting here that are reciprocating engines where we can also pull off waste heat. We've got natural gas turbines. A lot of the stuff is focused on being central plant equipment because we want to be able to compare that very quickly. It's also convenient because it's very easy for us to develop cost models, or it's relatively easy to develop cost models for what would it take to put this equipment in, and that doesn't change very much between locations. So if we're going to go for Presidio of Monterey on the west coast, or Fort Bragg, a couple different locations, all we really need to do is change the location multiplier for for costing, and we can still use the same generalized cost for these large-scale pieces of equipment. Okay, so we've got natural gas turbines, and the natural gas turbines with heat recovery. We have standard electric chillers that are air-cooled. We've got absorption chillers. Those are going to take waste heat and convert over to cooling energy. Those come in single stage that use a lower temperature, so this 200 to 225 Fahrenheit, and then higher temperature dual stage absorption chillers. You don't have to know what all of this equipment is. It's somewhat helpful to know approximately what it does. Again, it's some kind of a chiller, and that's in the name. And again, or partially, you should know maybe that this is used in conjunction often with something that produces waste heat. So if we have like a natural gas turbine, or we have a reciprocating engine and we've got a lot of waste heat, we're going to want to use that during the winter to heat our buildings. We may want to use it during the summer as well, and one of these absorption chillers to provide cooling energy for our buildings as well. We have higher efficiency electric chillers, so these are water cooled. So it basically gives you a couple different technologies depending on what the energy costs are, and depending on what their loads look like in general. Different technologies might be the most cost effective. Organic Rankine cycle turbines, which are very much like steam turbines, but are able to use lower temperature heat usually. And then a couple waste to energy technologies. Biomass with waste heat recovery, and just regular biomass for heat only. So we could produce electricity. So we have cost models for all of these things. Solar thermal. Then let's look a little bit further down. All right, so we've got steam turbines as well. So just taking steam and converting into electricity and some lower grade waste heat, starting with the higher grade waste heat. So we've got a lot of technologies here, and we can go into them in greater depth later on. I wanted to provide just an entry level to what this grid of data is and what it represents. It's not as complicated, I think, as it initially seems. It's just a little bit foreign to see it all lined up like this, but just a list of technologies and basic parameters so that we can judge the technologies against each other and use that collectively to make decisions for our group of buildings. All right, so for the centralized cluster, we're looking at the baseline. We need to enter in the equipment that it currently has. So every list as a default is going to start off with a couple pieces of equipment. The way that I've set this up, they always start off with decentralized equipment. And so the basic reason for that is so that you could rush through this process and get an answer very quickly without having to do anything. So you can just save the changes, go all the way through, and get some basic information on what the energy usage would be. Here, for the centralized group, we're not going to have any distributed boilers. Right? We're going to have a central plant. So we don't have any of those. This central plant is a heating-only plant, so we're still going to have distributed chillers. So this is information you would have collected as a part of the data collection process. So if we scan across, we need to make sure that all this information is correct. You don't have to worry about output capacities or any of the other information until you get over to the costing information. Now, because it already exists, you're not going to have any installation costs. You will have annual O&M costs. And this is a part that can be more difficult to get a hold of. You need to try to determine what the annual O&M costs would be for this decentralized equipment. Now, if you can collect records from the facility staff that are close by and they have good information on what the annual O&M costs are, then that's a perfectly valid way to go. That's usually pretty difficult to get a hold of. And we haven't been super successful trying to get a hold of that, at least at a planning level, to do it very quickly. So another way to go about this is to determine the approximate installation costs using RSMeans data, and then back out of that what the approximate O&M costs would be. And so I'm going to show a quick spreadsheet here this type of analysis is the kind of thing we would do to do this at least first order costing for these kinds of things. Now there are two main ways to do the costing using RS means that I'm familiar with. And the first kind of lightest level is to do a per square foot costing. So you can just get the number of square feet for that group of buildings, and you'll pick out your system type, and then you'll have a per square foot cost to add boilers for that building. So on a given building, it might be, or the number is approximately $8 per square foot for a boiler system, and that's going to include all the building distribution. And then you would multiply that up for a building to get the building level cost for that boiler system. If you're going to do it across the board for boiler systems for all those buildings, you would just multiply out by the square footage for all the buildings together. Now, we're not looking at this side, we want to compare the boiler itself, the heat source itself, to the heat source of working with a central plant. We don't want to compare the building distribution side. So that's a subsection of that total system. And so I'm going to cut it down from about $8 per square foot to about $1.50 per square foot for the boiler costing. And then for the chiller costing, it's a little bit more, about $2 per square foot, the portion that is the chiller, not the distribution for the cooling within the building. Again, the total cost is something around $8 to $9 per square foot. Now, that's pretty rough. And again, I realize there's a lot coming right now, so if you have any questions, go ahead and ask. But it's rough because you're not going to have the same cost on a per square foot basis for something in a southern climate compared to a northern climate. For example, a boiler. A boiler in Atlanta, that's where they've got a relatively low heating peak, is going to be smaller, and it's going to cost less per square foot than it would up in Detroit, Michigan, or something like that. So there's a difference there. But this is directly from the square foot, from RS Means per square foot costing guides. It's just a rough estimate that way. It's the easier way to do it for quick planning level numbers. The more difficult way, and I haven't added this in here, but I'm going to create a separate video, kind of training video for doing it both ways, the simplest and the more complicated, would be to bin out every building based on basically its peak, the peak requirement, and then you can separately cost off boilers for each one of those. And so you'd put them all in bins, and then you'd line up the costs that kind of in a separate costing guide that would allow you to do it that way, and then sum all that up and you'd have your answer. That takes more time and more effort. It is, it is a much better way of getting a closer cost number though. So going forward, I'll have those videos for doing the easier way that I'm going to show, kind of the light version here, and the more complicated route. But just to continue, let's look at, we need to do our chiller costing. So I've got boiler costing here and chiller costing. I've written down our two scenarios. We've got centralized and decentralized. We're working on our centralized scenario. I have the square footage already pulled out, and I'll show you where you can find that here in a little bit. And I've given an approximate cost per square foot. Now again, this could change, and we'll try to develop a range where you might even be able to select among that range depending on where your installation is located and that sort of thing. But it's just a ballpark. And if you multiply this out, square footage times the cost per square foot, you'll get a total installed cost. So that would be the cost here for chillers for all those buildings that square footage represents. It's the total installed cost. Now those chillers already exist, so we don't have to buy them. But if we're looking at the O&M cost, it's going to be some percentage of the installation cost. And this, again, gives us a pretty close ballpark for those costs. You can use a range of somewhere between 4 and 8%. And there's a reason for the range. About as soon as, if all these buildings were new and the chillers were all new, there's going to be a maintenance cost just to inspect them, do routine maintenance and that sort of thing, that's going to be on the lower end, something like 4%. If you're further into the life cycle, maybe you're 15 years in or 20 years in, and you've got units that are falling out and being replaced over time, this can also give you a way to add that in. It's really like an annualized cost for a large number of buildings where you can sum up that some of them are dying out each year, you're having larger scale repairs, and so you can move those numbers up. And if you actually have a really bad stock, it might be even higher numbers than this. So here I used a number of about 6%. We were somewhere in the middle for our stock here that we're looking at, and we can get a generalized number of about $212,000 for the O&M costs, the annual costs for all these chillers for these groups of buildings. So let's go ahead back over, see here, and we'll put that in, 212,000. Okay. Now, because we don't have an install cost, the lifetime doesn't matter as much. The lifetime is basically just annualizing the install cost. That's just an important note to make at this point. And we're going to need to save that. Before we do, we can go ahead and add in the central plant equipment. And I have to just tell you what it is at this point. If you were going through on a study doing the data collection, you would walk through the central plant, and this is how you would collect the data. But they have 4 of these 10,000 kilowatt units, central plant boilers. So because they have 4 of them, I'm going to put a 4 in the max number here. And they're 10,000 kilowatt each. We're going to end up, we could either just copy that equipment. I often do it that way. Let's go ahead and just copy it over here. If you copy it, it'll show up at the bottom of the list of equipment. And often I'll write in existing central plant boilers. This is a way just to keep it separate from the rest of the list of the equipment. So often we'll turn some of those other options on for the later alternatives. But here we're going to say these are central plant boilers that already exist. We already know the output capacity. That could change. We happen to have an equipment model for this size, but these are changeable numbers. You can go ahead and edit this if you had different size that was present in that central plant. You can find out what temperature those boilers output. Generally, they're all running on natural gas at this point for the installations. I think every one that I've seen so far, any boiler, we don't have them running on other things. Even if they're dual fuel, they're on natural gas at this point. We've got a nominal efficiency, which is very close to what just about every central plant boiler that I've seen so far, their nominal efficiency. Obviously, this changes even throughout the day for a boiler, but this is a good average number to use. Now, they're already installed, so there's no installation costs. We can get rid of that. It goes to 0. And you need to determine what the annual O&M costs are. And again, here, this is even generally a little bit more difficult. You would usually talk to the facility people that work within that central plant. If there's a plant manager, you could talk to them, or potentially the utilities, someone for the installation that works with the utilities that may know about any maintenance contracts or something like that. You can get information on the O&M. Now, this number, it's not related to the fuel that's used. It's only related to parts, equipment, and labor that are going to be used annually to maintain that equipment. So we've got a general estimate number here. Without any better information, we can go ahead and use the default values that are listed here, but they can always be changed either by whoever's entering the data or by installation folks on further discussions with them. All right, so those are the boilers. We don't have any chillers here. We don't have a chiller plant. It's just the boiler heating plant. And then we're going to go over to the storage tab. You can see there are 3 tabs here. We've got a lot of they've got this input-output name for the first one. And just generally that's related to having this direct relationship between the input, if it's natural gas or whatever is coming in, and the output. And so that's just the relationship for these types of devices. And the next tab, we have storage type devices. We've got chilled water tanks, hot water tanks. These are things you'd have at the central plant. And then the networks that distribute them tend to act like a storage device as well. There's storage, hot water, heating storage in the network itself. It's just a whole bunch of pipes holding all that water. Acts a lot like a storage tank that's also distributing the hot water. So we're in this tab now, and we'll talk again about the headings. We have pretty much the same headings here. Just a couple things that are different, and they might be expected based on the name. The amount of storage, and here this is an energy number, where the output was a power, an amount that you could do per time. And here we've got an absolute energy amount, so how much can be stored either in a tank, how much heating energy, how much cooling energy, and then similarly, how much heating or cooling is stored in the network itself. And then the amount of energy that you lose over time, which is kind of a different concept. So if you've got like a steam system, even if there are no, really any distribution system, but we talk about it a lot with steam systems, even if every building is shut off from that network, you're still going to have some loss in the network, and usually it's significant. And so that's the standby loss. We would say the amount of energy that's lost every hour in that system. Now, for modern hot water systems, that might be very low. We could have a very small amount of loss. It's well insulated. It's circulating. We don't have any major leaks or anything. For an old steam system, it could be huge, as much as 30% or more of the energy that goes in when there's very little load is going to be lost due to leaks and things like that. If it's a new steam system, it might be great as well with very little loss. But those are the fields that we're going to be looking at for these items. So we're going to go ahead and turn on the low temperature hot water network. In the walkthrough, we were able to find out what temperature the network was, and it most closely aligned to the low temperature. You can also select and change these. Again, the purpose, and this is maybe a little bit more detail, but the purpose of knowing these temperature ranges is related to being able to match up the right temperature with the technologies that can serve those temperatures. So we're going to say that there is a central network. There's one, only one exists. You would only ever mark one there. We're going to go across and say that these efficiencies are approximately correct. There is no installation cost. It already exists. And then again, you'd want to determine the O&M costs primarily from generally it's the same people, the central plant lead operators, and potentially anyone that works with contracting for maintenance contracts on the installation. And then we can calculate, and I'm going to try to give a spreadsheet that will help with some of this in the future, but you can get the general storage. It's usually small compared to any dedicated storage, but we can add that in here, and any standby losses. So we're going to go ahead with the default values here if we don't have anything better, and I'll provide some Excel spreadsheets to help you more closely calculate these numbers in the future as well. All right.
Hey, Matt?
Yep.
Mike here. What are the units on that standby loss?
So everything.
I might have missed that.
Yeah, it should have. It looks like it's just missing out. I'll make a note to get it up here. But everything in here, standby loss as well, is going to be in either power or energy. So here, this is in kilowatt hours, and it should be listed up here. We'll make sure we get it fixed in the future version. This is a loss per hour.
Kilowatt hours
Per hour, right? So it's similarly, you could just look at it as a kilowatt loss, a continuous loss.
Right. Yeah, I got it. Okay.
But it's a good question. It should be listed up there. Everything you'll find, and you should see units in all of these headings. It looks like we were missing one there, but everything is in SI units generally for this section. When you get to the results, you'll be able to switch back and forth the same way you were able to for the facility section. But otherwise, you'll see the main units here being in SI, just in kilowatt type units. I think one of the biggest things, it was important to have a single unit type here for clarity, and you wouldn't generally use something like BTUs to talk about chillers or electricity. That's commonly something you might use for heating systems. And similarly, you wouldn't talk about electricity or heating in terms of tons. So the only thing that the thing that seemed to make the most sense was to use SI units throughout. We're going to go ahead and save this. It should take just a moment, and then we'll go on to the decentralized, which is a much faster one to go through. And I think most of the ones that we work with will be decentralized. There's really a limited number of central plants generally across our installations. And I tried to enter in the clusters in that order, decentralized first. I wanted to handle it first, but it looks like it reordered these, maybe just alphabetically. Okay, so now we're working on the decentralized group of buildings, and we're talking about the equipment that's used to serve those buildings. So we're gonna stick with the equipment that is the default equipment here, the distributed boilers and distributed chillers. The only things we need to change, again, are the costs. So there are no installation costs, and that's correct. We want to go ahead and change the O&M costs. So we'll go back to that spreadsheet. We'll look for the boilers for the decentralized scenario. We've written down the square footage. We've got this per square foot multiplier here. We have the approximate installation costs, and then using that 6%, we get an annual O&M cost of about $127,000 per year. So we'll enter that in. Okay, and then similarly, so if we open this up, I realize it's a little hard to work in that smaller space. You might lose track. So that first line is for the boilers. The second line is for chillers. And again, none of the rest of this information. We've got a general efficiency. None of the rest of it really needs to change. We'll change this annual O&M cost. And going back over again, chiller costing for the decentralized scenario. Our square footage has been entered. Per square foot, total installation cost, and our annual O&M. So we'll do 169,000. These are rough numbers anyway, so you don't need to have all of the significant figures. Okay, and we'll go ahead and save that. Let's see, we'll just close this down. If we close it, that number should still appear in our grid here. It's just a visual aid to help, so it's a little easier to work in it. We'll go ahead and save it. It takes just a moment to save here. Okay, and we'll click continue. I'm not sure why it's detecting changes again. We'll go ahead and click yes. Actually, I think that's something, there were a couple issues that were recently fixed with this, and they didn't get a chance to publish out to the version that we're using right here. So I think that's just an issue that's been fixed at this point, but just showed its head right there. Okay, so now we're in the Constraints tab. And again, this is going to likely look a little unfamiliar. We're only going to use a little bit of this in the baseline. We're mostly just going to give an overview, and we'll come back around to it when we get back to doing the alternatives in the future. But I mentioned before that we can allow, we'll talk about this being an optimization, we'll allow the optimization to choose from different types of equipment, different pieces, all of that equipment list. You could change the maximum number up to something other than 0, and it could be included in the solution for one of the future alternatives. And when we get to that point, there are certain things that we might want to say our solution must meet. For example, we may want to have a 5 megawatt minimum electrical capacity. So we might want some technology to be able to provide us with at least 5 megawatts of power that can be used in the event of a power outage. If we want that to be part of our solution, to add that redundancy in, then this is the location where we would do that. So we want our solution to provide approximately this much amount of power at a minimum. You could always provide more if it's cost effective, but you could use this constraint to say the solution has to provide this much. There's a couple things that are good about this. One, it helps level the playing field when you're comparing different, say, system architectures. So if you're talking about a decentralized system with boilers and chillers everywhere, and you still need to meet this requirement, then you're going to have distributed, usually diesel generators. And because of that, the solution will select, because of this requirement that you put on it, the solution's going to select those diesel generators, and you'll have to be penalized with that cost. You'll have to pay for the upfront costs and the maintenance and operations costs. And if you're comparing that against a solution that's centralized and you have the ability to use the waste heat, then you could bring in, say, a natural gas-driven engine, and it would allow you to use the electricity from that, but also the waste heat. And it may be more cost-effective. The issue is, a lot of times in the past, we've compared centralized systems that have some high upfront costs to decentralized systems, but it's hard to weigh that electrical redundancy, where that may be a requirement, but we don't include the diesel generators in our costing. And we say, oh, look, the centralized equipment is much more expensive, and we're just going to decentralize everything. Oh, by the way, let's add all these generators. We won't add them in the costing. And so here we can look at those scenarios, compare them against each other with the same requirements. So that's the first requirement you can make a change to. You can also make changes to renewable targets, to the maximum carbon footprint. We have a project lifetime one here. I think we may actually phase this one out as well. But there's an interest rate, so this could give you a greater or lesser penalty on capital investment. Sometimes we just put this to the current like T-note, government T-note, and that would give you the appropriate government cost for borrowing money, something like that, which could lean your final answers on a life cycle cost basis more or less away from basically initial infrastructure costs. So I think it's an important one that we have some control over here. There's a net metering constraint, and this is important in a lot of our studies. Some places allow net metering and some do not, and so we can add this in here. It's also important if we're looking at a small section of the base and there's basically no other electrical generation, then that section of the base or installation could provide electricity for other sections, and it's much more cost effective if you allow net metering. So that one section that you're looking at updating could have some electricity production that exceeds during sometimes its own demand, and if you don't allow it to net meter, then you're going to have to basically just throw away any electrical production that's above its own demand. But if you allow net metering, which again saying that there's other parts of the installation that could use it, or you could net meter for the installation in general, then it's more cost effective. It makes all of the electrical producing, either PV or engines or something else, more cost effective. So that's a good one to control. There are situations where we can't net meter, and so you'd have to be able to shut it off to give a realistic look at what's happening. We have constraints you can set for maximum investment cost, and you can see some of these are just set arbitrarily high. So here we have this $500 million maximum investment cost. It's just set that way so that it doesn't really constrain the solution. But there are times when we're doing studies for groups of buildings, and we've used this even recently, where they've said, we've got a cap of about $4.5 million. For some reason, whatever financing tool we're using or whatever else, the cap is $4.5 million. We can't do any more than that. We'd like to do cogeneration if we could, but that's the most money that we can spend. And so we look at all the solutions that are within the space of things they can do that would be cost effective that don't go above that amount of capital cost. And so that's one thing we can control there. Similarly, the source energy constraint, this is one that I use more than, probably more than almost any of the other constraints, where we'll go through and do the baseline first, and then the base case. And I might say, if we reduce the energy usage from the base case down 30%, so 70% of the original, I'll put that source energy number in here and say that this solution, this new alternative, has to meet this 30% reduction in source energy requirement. And so that will give us a solution that meets it along with all the rest of the constraints as one of our alternatives. And we can just write that in as a 30% source energy reduction solution. And it'll show us the economics for that solution, how much more expensive or less. Generally, the least expensive solution is going to come out no matter what. So if we're amping up these constraints, if we make it more and more difficult to meet it, say we do a 50% source energy reduction, it's always going to get slightly more costly, but we can find out how much more costly is it. All right, and then maximum combustibles, this has to do with the waste to energy generation. We can generally just look around that area, determine how much of a combustible resource they have. And this might be waste from the surrounding area, waste from the installation itself, and we can enter those numbers in. It will help limit the size of the combustion waste to energy facility that we might be able to use. And then redundancy types. These are things that we're going to get into more again with the alternatives, but basically, if you're going to look at getting closer to a design of a central plant, you might want to do something like N+1 redundancy, and what that basically means is you can meet your peak with all of your equipment while one piece is offline. So basically your largest piece of equipment can be offline and you can still meet your peak. That's a standard type of redundancy that might be required for a central plant. And that might be so that you can do maintenance or something else, but if you're really going to design it, you're going to buy enough equipment to meet that requirement. And then if you want it to be a little bit simpler, you could just say I want a 30% additional redundancy requirement. So you can kind of toggle between these. I would suggest using the additional capacity redundancy type if you're just doing a simple planning study. These tools have been made, both the facility side and the installation side, so that you can do kind of the lowest, the kind of a planning level, and then if you want to, you can go into greater detail. And I've shown a little bit more detail probably than you need for the planning level already, and do something closer to a design. I saw just another call coming in. Okay, and so that's kind of where I would go there. So for a planning level, just do this additional capacity, where 1 is just unity. That's just going to be standard amount of capacity, and if you want 30% more capacity, you would do something like 1.3. or you could do double capacity or anything else, but this just gives you an easy way. And if it's at 0, it's basically just shut off. There's just no requirement on additional capacity. You still have to meet all of your loads, but there's no additional requirement. All right, so we'll save these. And we basically didn't do anything for these because this is the baseline. This is the as-is situation. We don't want to require any additional things to happen, any additional equipment we purchased or anything else at this level. We just want to run through with the stuff as it is. We'll click continue. And here, just like the simulation page, this is the optimization page. This is where we're actually going to be running for solutions. I'm going to drop this down. It's too bad it doesn't start off that way. Maybe we'll fix that going forward. And then you'll be able to see the list of alternatives and then the list of building clusters. That's the language we use, again, just for groups of buildings. So at this point, we only have the baseline, and we have the 2 clusters underneath that. If you want to run all of them, you can hit this optimize button here. There's just a couple buttons that you can work with. The optimize button, you could also individually click the optimize. You can click it on an alternative. It will do all the clusters within an alternative, or specifically on one cluster. So just a little bit on how to use this page. Similarly, you can reset all of them. This doesn't seem important at this point, but when you have 8 or 10 or 20 of these, then it's much easier to use some of these other buttons to do them all at once. We'll go ahead and run them. And they really often don't take long, especially for the baseline. When you get to more complicated alternatives, and again, if you were trying to do it, use it for something closer to like a pre-engineering or either feasibility or something closer to design where you're going to be looking at a larger solution space, then it can take a little bit longer. But these, it looks like one is already completed. One was queued, and then now it's running. You can see these status symbols here. And it'll probably run for maybe a total of 20 to 30 seconds. It's already done. It's now in the polling stage, which means that it's pulling data back from that server where it was actually run. It's run on this server farm to speed this up for everyone. It's not run locally on the machine. And we're pulling that information back. And actually, you can see this lit up already. It went from gray to this black. You can always click this refresh, and that will refresh the list, kind of the symbols that are shown for each one of these that you're running. Again, for a larger group, it's more important. But once it's completed and pulled back from that polling, then you'll be able to continue on to results. So we'll click continue. And the main one I use out of these reports is the equipment overview. All right, so something went wrong with the centralized group. I'll have to go back over and look at that quickly. The decentralized, we'll open this up and we can see the equipment that was chosen. We have the distributed boilers as we expected, distributed chillers, and the AC bus. So it's not too interesting here. We would normally see something else for the centralized. Let's go back over here and see if I left something out. So I'm going to go ahead and make sure that this was turned on for 4 p. Oh, that's why. Okay. So we selected this boiler, and I thought that I set it to 4. I set the first one to 4 and then put it back to 0. And it looks like I didn't end up saying for this group of existing central plant boilers that we had 4 of them. So I created this new, this new line of equipment, these boilers. It was still at 0 because that was the default, and I needed to change it to 4. That was the amount that they had actually in the central plant, and I didn't do that for whatever reason. So we'll go ahead and save that. We had a few changes. Originally, just as some history, these names were all kind of super truncated, basically because I was the only one that was using it early on, and it wasn't as much of an issue. And as a part of this process, the names didn't used to be able to contain spaces. They were just a limitation. And so recently we went through and made it a lot more user-friendly. That may sound like a surprise. It may not seem that user-friendly, but it's much more user-friendly than it was. And through that fixing process, a few other things came out of that, some bugs. And so we're working through touching those up now. So I went through and saved, now that we have 4, those 4 boilers are present there in the central plant. And I'll open this back up. the decentralized had already run, so it looked over and saw that that was already complete and brought back those results as successful. And now we're just running the central plant one. We didn't have to go through and touch anything else up. We just had to save that one piece of equipment. And again, 20 seconds or less, finished up. It's in the polling stage. And we should see this turn black very soon. So everything is done now, it's just pulling it back. So this isn't even really a computation time, just transferring data. We want to wait for this to turn black. If we click continue here before it turns black, we'll probably be shot back to the details. You can try it. Yep, so shot back there. But there, it turned black. So just a few extra seconds and that will open up. It's just the software realizing that all the results are back and now it has what it needs to create these reports. And you can see now that this has many more devices. So it's basically telling you how many of those things that were available in that equipment list have been selected for the lowest cost solution. And we could talk more, I think, maybe even in the future about how that optimization works. There's a limited amount that needs to be known. I don't want to make it particularly complicated here, but let's look through the list. So we'll always have this AC bus. We also have it in the decentralized option. This is really just the substation, connecting out with the rest of the grid. It's just not necessarily something that you need to focus on. It's always going to be there. It's important, again, as you get closer to something, coming closer to a design where you may not have a large enough substation if you're looking at large-scale equipment, and that may need to be changed. So you could potentially put a second AC bus in with a different maximum power throughput, and that would have a cost associated. So you could do that in your study later on if that was an issue. Usually it's not for most of the work that we're doing. So we're looking back up here at the centralized group. We have those distributed chillers the same way we do for the decentralized group. And then we have the 4 existing central plant boilers with their capacity. Heat exchangers that are just dropping the heat down from what it comes from the boilers, dropping it down to the temperature of the network, and then the network itself. So all the equipment we'd expect to see, nothing exciting here. This is going to be more exciting when we get to the alternatives and we let it do an optimization with more equipment options, and we'll be able to see what other technologies would be cost effective, and then you can analyze them here. So we'll close this down and go to the next step, to the decision analysis. And for me, these work hand in hand. I go right to this summary report. All right, opening up the summary report, I'm going to use the magnifying glass again here because there's a lot of fields. Normally, we would have the rest of the scenarios showing up down below here, and you'll see that there are zeros here because all of these are in reference to one of the scenarios. Let's go to close again, and you can choose which one. So if we had a list of alternatives, this would be longer. We would have more items down here to choose from, and you can choose which one you're going to compare it to. And that becomes interesting when you want to compare the energy savings. Often we compare it against the energy savings for all of the alternatives against the base case. That's the future case that we're comparing our future alternatives against. Where the baseline, we're primarily looking at making sure we have an accurate representation of the current reality for that installation or that region. So let's click the plus here. And we can see the 2 groups of buildings are 2 building clusters, the buildings that are centralized currently, and the buildings, I didn't shut off an investment somewhere, and the buildings that are decentralized. So the investment shouldn't be showing up here. I'll have to go back and look at, there must be a section that I didn't shut off the investment for or turn to 0. We may have had an issue saving something, and that may be why the 4 didn't change over. I bet that's the cost for the boilers. So I'll go back to that in a minute, but we've got the total equivalent annual cost, the source energy, which you can see is actually very similar, the site energy as well. And one of the things that I like a lot about this table generally, and you don't have this option, something that's going to be, say, in Word, at least not to my knowledge, but with this interface, you can actually blow up this in the these headers as well. You can click on these and you'll see that this alternative, information about this alternative, is stored here as well. So each alternative has a certain number of facilities, and we can quickly look at that. So we can compare. The centralized group has fewer facilities, but as a whole, they represent a greater amount of conditioned square foot area. So you can compare those that way. You can also look at the square footage and compare those numbers to, for example, the source energy, and see that even though this has a much larger amount of space, the source energy is actually lower. And just all the way through. Now we can collapse that back down. Again, there's so much data that's captured here that you may want to switch between a few of these. You don't necessarily want all of them open. That's why we made them collapsible. You can look at the investment. Now all of these should be zeros, and I believe this is for the boilers that there was some issue with saving at the time. And so you'd be able to look down the building investment dollars and the cluster investment dollars for all the scenarios as we go forward, and broken down between the building clusters. We'll collapse that again and look at the total equivalent annual cost. We're going to have a portion of that due to energy costs, and that shows up in this column, and a portion of the annualized cost related to building upgrades. And we didn't do anything there because it was it's the baseline. We're not talking about the things that are going to be done in the future. That'll be talked about, or that will be described in the baseline and then the alternatives. And then the cluster costs. So this is going to be the annual O&M as well as the annualized investment cost. And that's what's making this one look larger. So that's most of it. We can also, again, most of these are zeros because they're in comparison to some other alternative. But the total site energy as well can be broken down into the electricity portion, the fossil fuel, any biofuel, and we separate out the amount of electricity that was purchased to make it easy to assess that aspect. Here, all the electricity that was used was also purchased. In some scenarios where we're producing electricity either from solar or wind, biomass, natural gas, cogeneration, something like that, then you would see that some of the electricity that we used wasn't purchased. It might say that 0 has been purchased if we produced all the electricity. So those are kind of important things to know about this table of results. So that's most of the information. It actually took longer than I might have expected. There are a lot of details there, and I know this is the first time that we've hit this for a lot of people. So it'd be nice to have a fair amount of question time.